I'm Sasha Karpinsky. I work for Uploadcare. Let me remove the cursor. Since recently, I am one of the developers of the popular Pillow library. Maybe not all of you are familiar with it. It's a Python language image library, and I'm also one of the makers of the Pillow SIMD library. Today, I will speak in two capacities: as a library developer and as the author of an application using this library. So I will be telling you about my occupations, and I will tell you about the use of Pillow and other Python-based libraries. For Uploadcare, I deal with on-the-fly image processing, where the image indicator comes, which should be done for the user, and the service tries to do it as fast as possible and then provide an answer for the user. In most cases, the client is the browser. The whole service can be described as a wrapping of the graphic library. That's why its speed, reliability, and easiness, easy to work functions are useful, and we use Bacid as the graphic library. To be able to tell you the other details, I need to describe the libraries I'm going to mention today. I will start with Pillow. Pillow is the PIL fork Python imaging library. You might have heard about it. It's quite old. It was prepared for Python Python 1.2. Then at some point the development of that library was suspended, and a team of developers decided to develop a fork for Python imaging library to be able to run it on modern systems, because by that time it was in such a condition that it wasn't easy to use it. That's why PIL fork was upgraded, and after a while a certain number of upgrades arrived at a critical mass, and therefore Pillow 2.12 came, which supports all today's Python versions. Pillow SMID is a fork library, or rather it is a replacement of one library with another, and those upper transactions that were rewritten start running fast, and you don't have to change not a single row of the source code. And SIMD is a single instruction multiple data, where the processor performs more actions over the same time. Pillow SMID can be now assembled using instruction SSE4, which is the most widespread instruction set now, which has been in use since 2013 using AMD architecture. And today I will also mention OpenCV, which stands for Open Computer Vision. It's a library with multiple functionalities for analysis and computer imaging, and besides that, it also has quite primitive tools to handle images which are available from common graphic libraries. OpenCV uses C, but it is evergreen because it uses all the library functions. Unfortunately, it doesn't support PyPy and only C data. VIPS is quite an old library, and there was a time when it was ahead of its time because it was based on very good principles to the effect that to handle large applications, we don't need to store them in memory, but rather we can handle certain parts of it and then switch over to the other parts. Today, for VIPs, there are lots of binding for today's languages, for Go, Ruby, and Node. And for a long time, there was quite a strange binding for Python, which I tried to assemble, but it was too difficult to install it. Fortunately, the situation has changed. A couple of months back, binding for PIVP was released, which is easy to handle, and accordingly it supports all Python's versions which are used today. We should also mention very famous libraries such as ImageMagick and GraphicsMagick. ImageMagick with time just obtain the same functions as GraphicsMagick, and it doesn't matter which one of them you use. For mathematics, for ImageMagick, we have binding image 1 implemented on C-type, but it hasn't been updated for a long time. For both of the libraries, there are binding PGMagick, which has more functions and is implemented on Boost Python. That's why it doesn't have PyPy support. Honestly, the key thing that I am looking forward from graphic libraries is performance, because performance is something that does not make it possible to say which library works faster than the others, because it depends on the functions, and even the speed of the same function may change due to some external factors or conditions. That's why it would be more correct to speak about the speed of a particular transaction or a set of transactions important for your own application. So you may do it just for yourself to assess the needs. However, when you do this benchmarking, it's important to monitor the result of the output of the graphic library in order not to make a mistake. While preparing for this presentation, I found an article with the code shown there with box filter. In both cases, the parameter is 3, but the result is different. So the trick is that with PyRL, it stands for the radius, and with box CV, it shows the diameter, and the right value for box CV would be 2 plus 1 in both directions. Why is performance such a problem for a graphic library? And why do we need to think about it? The thing is that any transaction that we perform using a graphic library, its complexity depends on a number of parameters, and the most evident of them are the size of initial image. If we magnify the image by a factor of 2, various dimensions increase, but they're not the only things that change. For instance, the Gaussian function has the parameter of radius. So this parameter with a radius of 3 takes 58 milliseconds to get dim. If it is 880 milliseconds, then it is 10 times longer. Then we arrive at cubic complexity, which needs to be taken into account in your application. That's why when I had to add the Gaussian radius to my application, I started looking for the algorithms making it possible to achieve it over a short time. So I found it and I implemented it using PyO. And with PyO, the radius of dimness or haziness does not affect the transaction. That's why it is possible to add this transaction. The most frequent transaction we need for images, to my mind, is excise. This graph of resizing, or the graphic of decrease, is 8 times, and for pattern engine library is 1.25, and the performance, if the reduction is 1.25, is 17 seconds. Just to give you an idea, if you take a photo from an iPhone, then you can, with 12 megapixels, you can imagine that it can be reduced in 1.25 seconds, which is quite a lot. And when I started working on resizing, just optimizing it, then I managed to double the speed in Pillow 2.7, and by a factor of more than 2 for Pillow 4.3. Many graphical transactions are well supported by SIMD. With Pillow SMID, the performance is 15 times higher than with the original Pillow version. And here, just for comparison, is the performance of OpenCV. But I need to clarify that it is not quite a correct comparison, because OpenCV uses a box filter whose quality is a bit worse. With the Pillow SMID, the quality is better. And here you can see an incomplete list of transactions which are sped up using Pillow SMID. Before that, I told you that we cannot say that one library is several times faster than another one, but we can do our own benchmarking for the transactions we need in our application. Here I did the transactions that I need, including load, rotate by 90%, by 90 degrees and so on. And the performance with Pillow SMID is twice that of the original Pillow, but with OpenCV and VIPs, which should also run quite fast, their performance was even lower than with the original Pillow, which was quite strange. I tried to look into the reason for it, and it turned out that the simplest way to use OpenCV is to use OpenCV Python. This is a binary assembling based on the slow version of LigiPack. While with many systems, for instance in stable band, LigiPack Turbo is available, which runs much faster than if we use it, then OpenCV results would be much better. As far as VIPs are concerned, I have been in corresponding with VIPs authors. We corresponded for a long time, and he found quite a few places in the VIPs where the performance was not based on optimal routes, and he promised to correct it in the other versions. If we look at the source codes, and then the results would be quite different.
So, what conclusion could be made? If something is working at a certain speed, it doesn't mean that it will be working at the same speed with you, so you will have to check the application in the current environment. So the benchmarks that I have shown could be found at this page. I make the benchmarking of certain libraries, and there's a repository where you can see how the benchmarks are implemented, and some solutions are offered, libraries or additional benchmarks. So that's how it is. Another important issue when working with graphic libraries is concurrent work. We know these systems with multiple kernels, and we do not need to use one thread. And I might disappoint you that Pillow is the only library where it is not possible to use multiple threads with kernels, and let me explain you why. I've been talking about performance and performance per kernel, and we are interested in two metrics of performance. It is the actual execution time for one operation and the throughput capacity of many operations within the framework of one system. And the first metric is important for this topic. There is a user that makes a command and expect execution. Then the throughput is important with the server, because the users are many and the hardware is limited, and we strive to pay less for it. So, based on these two metrics, we can look into two options of concurrent work. The simplest way, when we know there are many operations that do not depend on one another, we can launch them in different threads or in different processes, different pipelines, and the real time of the operation per se will not change, because that's how it will take, but the throughput of the whole system would be increased. Another way of concurrent work is at the level of the graphic operation. That's what is implemented at the level of the library. When the command is given to a library, it itself splits it into a number of the threads, launches them and arranges them accordingly. And the time for one operation is reduced, but the throughput is growing, but not drastically with respect to the capacity we have, because it's not possible to split each operation, and there are certain overheads that exist. And another way is SIMD, and in this case we both lower time and increase throughput, and we can compare it with the regular optimization, and in this case it is a win-win approach. All those methods could be combined. but it's possible to do without combining. SMID could be combined with concurrenting both at level of operations and applications, and it is not possible to combine it at both operation and application because it is useless. You will enjoy not the benefits but the drawbacks of all the approaches. The time for operation will be the same, but the throughput will not be high. So when we talk about the threads, we write in Python, and you know there's a global interpreter lock that does not allow two threads concurrently. Python is allegedly single thread language, but it's not true because GIL limits the execution of two Pythons, but it is possible to use other languages. If we draw some other language in the Python, it can release GIL, and some other operations that could work in the same process in the other threads. And reference the libraries that I have mentioned, all of them release GIL, and they could be used in the multi-thread application. PG Magic does not release it, unfortunately. I've raised an issue with the authors, and I think they will sort it out. Reference the multiple threads. How can we possibly address the issues that we face? Here is a task, for example, to process thousands of images. We can generate thousands of threads and put thousands of images, but it won't be efficient because they will clog all the CPUs, and I have formulated rule number 1. We should not create more than n+1 workers, and in this case n is the number of the kernels or processes where the application is used. For example, we might have n+1 of Tornado, and the balancing is done by engine Nix, and it works like that. And if we start talking about Tornado, then I think it's a good idea to use the concurrent frameworks together with the image processing, because when the images are being processed, when the operations are executed by the CPU, it is important, it is wise to make input and output. But if we draw the graphic operation, it blocks event loop, and there is no output, even if the library releases GIL. And it is possible to overcome it, and it is enough to make a separate executor on threads. The library will be launched over there, the GIL will be released, and the event loops will be working just all right, and when the work is over, the controls will be resumed. We are replacing call at asynchronous, and the event loop is working just fine. Another important thing related to graphic libraries is file input and output. It is very rarely that we draw an image in the application. Mostly the task is to open image sent by the user, and it has some kind of graphic format. There are many of those, and there are certain issues, problems, and we need some kind of tools that should be available in the graphic libraries. And the first is lazy loading. And if by means of a PL we try to open an image, it takes a little time, and there's no decoding happening. But we have an object, image, we can read mode. It is RGB or palette, etc. We can read the size in pixels, we can read some meta information, and we can make up our mind whether we're ready to decode or whether they try to bulldoze us with a mega picture. If we take a decision to work with the load, we call the mega load, but of course it should be called in few cases only. Another important tool when we work with graphic files, it is loading broken images, because pretty often the images that are loaded into the systems are broken. There are errors of the network of the coders, and so if we try to open it by means of PL, and the PL tells that the file is damaged, we can switch on the broken image mode, and the PL will try to ignore all the errors. All the non-fatal errors will be just disregarded. And in this case, it's quite possible that it won't be possible to restore the image in full, but we might show this image, and it will be much better than the page with an error. I have made a table which is related to input and file input and output. I have calculated the number of the codecs and other features, and it turned out that the OpenCV has less codecs, and the IAM has a lot of codecs. Pillow is somewhere in between, and WIPs, though it's 12, but WIPs can use image magic as an intermediary link to open the formats that it does not know how. And I didn't check how it works. I hope that it can work seamlessly, and you use WIPs to open the image, and it's doing all the rest. Hopefully, this table is interesting, and there is no auto-rotate of the images depending on the orientation EXIF. If you have been working with JPEG, you know that they are not coded in the orientation that should be displayed, and in the ZIF tag there's an orientation which should be applied to the image after its decoding. Pillow does not do that automatically, but Pillow can read EXIF, and it can rotate the image accordingly, so it's easy to go around it. If you can look at this table attentively, you can see that OpenCV has got less features of all and less codecs, and OpenCV also has got some other quirks. If we try to open a certain image, and if we don't know what's the image, if these are JPEG, they turn it based on EXIF, but it's long file, it ignores the alpha channel if it's PNG files, and strange things, and it shows flag im read unchanged, and it stop rotating JPEGs in compliance with EXIF, and it is one flag that is responsible for it. Who is the person? It must be one person that is responsible for it. Who is that? We can check the credits for it. If we don't know what's the format of the image, and if we need the alpha channels for PNG files and EXIF, but nothing could be done about it. And if you look at those quirks of the OpenCV, flags, no lazy loading, odd flags, no access to EXIF and ICC, and try to think why, the answer is just there. OpenCV is not a library. just like a pillow, which is needed to use with the user content. It is a library for computer vision, which ad hoc receives data in a more stable format. Like if you have, say, the CCTV and it saves the images in one format in all without no variability. You just set it once with OpenCV and that's it. But what should be done if the application is working with the user content, but on the other hand you need all the power of the OpenCV to recognize the image. In this case, you should combine the libraries, and in this case, Pillow has got an opportunity to export the images to MPy array, and it hasn't got its own format. It works with the arrays, and by converting it into NumPy array, you can work with it as OpenCV, and we open it with Pillow, and we do certain things which are convenient to do with pillows. Then we do some magic with the OpenCV, and again by means of Pillow we can convert it. We convert the array back into the array that the Pillow can be working with. So that's what I meant to say. Thanks for your talk. You said that you optimize the image processing by multi-threading in Python. But the image processing is the code that have overheads of the CPU. Why not rely on the multi-processing? Because, as you have said, the GL is single thread in Python, because Python is not a thread-safe language. How to synchronize the threads that start the libraries that you have listed in the multi-threading approach?
The first part of your question is, why is it that I don't want to rely on multiprocessing, which was intended for CPU distribution? Do you mean the Python module for multiprocessing? There isn't such a big difference in using it. Just that, well, the gentleman from the audience is not using a microphone. It's impossible to translate his remarks. They're not using the microphone, so translation is impossible. Oh, yes, I got you. I got what you are driving at. Right here, just to release GIL, just for the runtime of the transaction, that is to say, while the graphical library is running on an image. It doesn't need any Python structures, it doesn't need any interpreter. It may go on running while the Python interpreter is busy doing a Python code, and by the time it is over, it just invites GIL, and this is why unsynchronization occurs. And as far as the use of multiprocessing is concerned, there isn't such a big difference. Possibly we can use it too. Just that in our case, in our production, we just launch N+1 rule, Tornado. Each worker is a separate interpreter, which uses non-thread mode, but we simply don't need it. But you may use multiprocessing to distribute between different transactions. Thank you. Have you ever tried to run your library on video cards? It's impossible to run a library intended for a processor using a video card because it would need an absolutely different platform. And I could actually generalize about it, why we do not use video cards for handling video images. As a library author, as I say, I'm just providing an answer in my two capacities. In this case, we would have to transfer all the calculations onto the video card, including coding. And for this purpose, a lot of codes would have to be made. And this would be quite difficult, because if it is JPEG, it is possible to code and decode it concurrently, but with PNG it's impossible. So PNG file coding and decoding would run at a turtle speed. That's why the whole infrastructure for processing would be too difficult to move over to the video card, but you could copy them from RAM. But in this case, the speed is limited by the performance of the port, and its performance rate, if I calculate it correctly, is 11 gigabytes per second, while with memory of state-of-the-art systems it is 25 to 35 gigabytes per second. That's why in many cases running on the same nucleus, the limitation is provided by the memory. That's why if we could actually increase it by a factor of 2, if we move huge arrays across it, that is to say, there are lots of calculations, then it would be worthwhile, but when handling images, it's not worth it. Well, in your overview, somewhere in the middle of your presentation, when you were describing various things related to safety and security, which is safer, which is more secure, and what additional checks need to be done for downloading. I mean, if it is a user file, then they can, roughly speaking, use the vulnerabilities. In that meaning, that's right. I can honestly tell you that ImageMagick, as the most widely used library and the oldest one too, it seems to be the most secure one, if this is what you are concerned about. But otherwise, it is actually possible to find vulnerability about any library. Actually, certain vulnerabilities are detected on a regular basis. Vulnerabilities are always there, and they are always found after a while. To my mind, it is magic, but it's my subjective opinion. Any more questions? Good afternoon. Thank you for your presentation. My question is, what are the drivers of performance in Pillow? First of all, it is SIMD. Is it just a general question? You showed the graphs to illustrate that it is always faster. First of all, it is through the use of SIMD, because there are more operations per instruction, and besides, it is strongly optimized. Roughly speaking, a lot of hours were spent on its optimization. But why didn't you provide it with a pull request? Then it would be faster. But actually, I introduced the same changes with PO, with Pillow, but I don't think it's still possible to apply SMID within the framework of Pillow. I believe there are several barriers to it. First of all, it needs to be developed. Somebody should come and do it. But this is possibly not the key obstacle. Secondly, Pillow is a cross-platform library based on ARM-stations, and that's why it is only possible to accelerate the performance through x86, and we don't know whether it is really needed. And thirdly, it is that this code is kind of compiled using the machine where it is run, where the speed is maximum. But with Windows, it is not the case. There it is compiled on one machine, and then it is run on 1,000 other machines. And so if a machine doesn't have the necessary instructions, it needs to be implemented additionally. And so nobody has come asking for the opportunity to run it on Windows. If you have a desire and the resources to do it, you're welcome. Any more questions? I just wanted you to elaborate something. As a matter of fact, the problem is that we need to put in a large number of branches, and it means that the whole code is compatible with itself. What we need is just to merge it correctly. But another problem, which is due to the use of Python, is that Pillow for Python is assembled using setup tools, and when we use different instructions, it is quite desirable to be able to use different compiling flags. But in the other case, to my mind, it's impossible to do. At least I haven't researched it yet. But they say it's possible. I'm ready to speak to the people concerned to see whether it is possible to implement. Any more questions? It looks like there are no more questions, then thank you very much.